Well, thank you very much. We will see whether everything they promised you I can really fulfill here. But some parts are really kind of quite interesting, and I cannot really complain. I was picking the right field of science. I made one big mistake. I was doing ultra-fast spectroscopy in Hamaguchi's lab, and I said, this stuff is leading nowhere. That was not my best prediction. But then I went from from ultra fast to ultra small, and okay, that was a very good decision. Okay, so molecular spectroscopy at the limit of spatial resolution. Obviously, this is about length scales. You can find lots of these graphs in the internet. I picked that for no particular reason, except maybe it also represents a lot of the stuff that we are doing. We try to push lateral resolution, but a big part of our research is also involved in how to apply that to small systems. So a cell is borderline in our case. That is already pretty big, but subcellular components, for instance, or bacteria, virus, proteins, small molecules. And as I wrote in the abstract, actually almost all processes, they ultimately happen in chemistry and biology. They happen at a molecular level. So two molecules kind of make a bond or break a bond. So can we really follow that up? Can we really go down to these dimensions? And that means you have to have a sensor. So the naked eye, okay, at 10 meters, it goes further than 10 meters, but that's not my graph. Light microscopy, yeah, that goes beyond micron. With special extensions, which are also called nanoscopy, the fluorescence-based nanoscopy, you can go down to, well, a little bit optimistic to a nanometer, maybe 5 to 10 nanometers. But essentially, this is still diffraction limited. By clever arrangement of two diffraction limited beam, you can go beyond the normal diffraction limit. And in the end, who cares? You want to have a high resolution. And then there is also electron microscopy. Electron microscopy is already a big step because essentially everything you can put under a microscope, almost everything. But for electron microscopy, you need ultra-high vacuum. Sometimes you need even a cryosystem to have very high resolution. But this is the cost of the high resolution. Very useful technique. We often use that, but in a way, this is a different way to look at a sample. The way we see that, this kind of nanoscopy is really approaching, or when I started, it is really approaching dimensions where things happen, where chemistry, biochemistry happens, where a virus would bind at a cell. And that was, for me, very fascinating. And I hope I can transmit some of this kind of fascination also to your audience. And then what you said, very true, very true. I mean, it really looks like that. I don't mean the memorial, I mean the house behind that. That is house of the university, and this is a listed building. And if you are a university and have a listed building, you are in trouble because you have to kind of renovate by your own. So that will last some decades, I guess. That is pre-COVID, but the important part is written in stone here and will not change so quickly, I guess. This is the diffraction limit. So this says how close two objects can be that you can just identify them at different two objects. That has to do with the wavelength of the light that you're using, with the refractive index, and with the collection angle. And if you want to have better resolution, usually what you do is you play with the lambda. In a way, also you could envision electron microscope. It also plays with the lambda, but of course this is not quite right because charges also kind of reject each other. But essentially, you need high energies to get to high resolution, or you have to play with the refractive index. But then came an interesting person, Hachi Synch, and he was in contact with Albert Einstein with letters. These letters can still be read, still in a museum. And he proposed to Albert Einstein, I found an easy way, I think, can break this diffraction limit of Hubble by just making a hole in a metal screen which is smaller than the diffraction limit, and then bring the screen very close to a surface. So close to the surface that no diffraction can happen, so I'm not diffraction limit. Einstein? Yeah, that sounds very interesting, but is a very theoretical approach and will probably not work in practice. I have to give it to Einstein. He was right. The GPS was put into practice earlier than a near-field optical microscope, but it's a bold move. I think you have to have a Nobel Prize to say I said, this is not an unpractical idea. But it really works, and it took until 1983, if I remember correctly. The main problem was you have to have an aperture, and you have to bring this aperture very close to a surface without breaking it. Very practical problem. The idea as such, you could probably even make such an aperture, but that was the main problem. So what they did, that was before the AFM was invented, just 1 year or 2 years after the STM, the tunneling microscope, was invented, they used tunneling contact, and then they crashed the tip into the surface. And I think tip number 4 or 5 had then a nice aperture, and then they were using to scan it. It was a group at IBM, Rüschlikon, who showed that concept. And that was actually, after that 20 years, that was the state of the art. You used tips where you squeeze light through an aperture, and then you have your sample here, and then you measure either transmission, reflection, or even go back to the tip. And I think about 50% of the papers were how to make the best tips. I've been there. Then people thought about a different concept. Consider this as a kind of passive approach. You squeeze light through an aperture. And here in that case, you illuminate light from outside to a sharp tip. And on this sharp tip, there is a very small light emitter. Could be a single molecule, could be a sharp edge, could be a metallic edge. And even a silicon tip as such was shown to show a contrast. It takes forever to measure that, but even with a silicon tip, you can get a contrast. And that means you can distinguish where the tip is and where the rest of the focus is. And that is what you want to have or what you need for high resolution. Okay, let's stick with a bit with history, how it was done in the beginning. So we used kind of so-called aperture tips. And here is a very nice example. And here is a very small aperture for that. So the problem with that aperture is a transmission of one photon in 1 million photons. So you lose essentially 1 million photons before you get one out. Increasing the laser power will not work because you will then melt the aluminum. So we also played the game, kind of making tips, and you see we had a different angle here. We had a kind of more shallow angle that helps us to get higher throughput, and we managed to get 1 photon out of 1,000 photons out. Yippee, celebration, much better than before. But well, it made a big difference because then we could arrange a kind of a marriage between my 2 heroes here, Haji Sunj and C.V. Raman, because at that time we had then enough photons to do also Raman spectroscopy. And just a quick reminder, most of you know, I'm sure, about Raman spectroscopy. So essentially what you want to probe with Raman spectroscopy are vibrational levels. You could also probe rotation levels or electronic levels, even atomic levels. But that is what Raman spectroscopy is famous for. And you could do infrared spectroscopy, so simply excite from the electronic ground state, vibrational ground state, to the first excited vibrational state. And if your wavelength is right, you have an absorption. Or you do that detour that it goes to a so-called virtual state, so you are far away from the electronic state, and you go down to the first excited vibrational state. Because you know your excitation laser and you know the laser that's coming out, you can then reduce the vibrations. This goes, okay, also in the other direction, Boltzmann distribution. If you already are in the first excited state, you get a so-called anti-Stokes photon. Interesting thing, I will not go into detail, but this is very useful. With that system, we can, for instance, detect the temperature and the laser focus by just applying Boltzmann. Then there's also resonance Raman. Many people would say, though, if the signal here is not enough, you simply do resonance Raman, because here you have real levels, which is true. But there's fluorescence, there's luminescence, there's simply burning of your sample. In some cases, you are very lucky, and resonance Raman is very efficient, and then you should do it. But you have to expect surprises if you go to unknown systems. So the advantage of Raman spectroscopy is, of course, like any vibrational spectroscopy, you get structural information. You can operate in a nice wavelength range where you literally see something. Very easy sample handling. In geology, it is very often used to put your rock under the microscope. You don't have, I mean, try to do infrared spectroscopy with a rock. It has a decent lateral resolution limited by the diffraction limit, but here, low sensitivity. So low sensitivity in terms of an analytical tool is, of course, not the best news, right? On the other hand, as I like to say, it is also good because you can see your neighbors, you can see me, and if Raman would be efficient, you wouldn't see me. Because all the molecules between us would do Raman scattering, and so the light would be everywhere and then absorbed again, and it would be just a blur. So it's good that Raman is so inefficient, but not as an analytical tool. So Raman intensity, we want to increase. So we have the intensity of the Stokes beam is defined by a constant. Then we have the incoming intensity. Then we have here the frequency term, which goes to the force power. That would be nice if you could use that all the time, but just use lower powers, not lower powers, sorry, lower frequencies. And then here is the Raman tensor. Here in normal Raman spectroscopy, we cannot do a lot with that, but with resonance, we could do something with that. So the problem is with this kind of going to the UV will yield much more photons is a bit problematic, because then you also go to resonance Raman, and again, sample burning. That's no free lunch here. So, but if possible, that was a kind of one of the alternatives that we are trying in the beginning, resonance enhanced. And then there is a so-called surface enhanced Raman effect. Where is that here? Essentially, that's the incoming intensity. And it's not the incoming intensity from the outside lasers, it's the intensity that's generated at the site of your sample, for instance, when it's sitting on a rough silver surface, or as we see later, if we apply another trick. That proved to be very efficient, so it allowed us to get high sensitivity and high specificity, and we could put it through a small numerical, not small numerical aperture, a small aperture, and get high lateral resolution as well. I show you only one of these dated experiments, because this is really one of the last experiments that were done, and you will see the reason very soon. So I have here 20 by 20 data points, 100 nanometer step size. So then here is always the full Raman spectrum. When you go to so-called 0 centimeter -1, this is just a reflection. This is a very rough substrate. You have a silver substrate. I'm sorry that this is kind of squeezed so up here. You have a rough silver substrate to get this enhancement. There is labeled DNA on it, and we scan it with an aperture probe. Then, of course, we go to inelastic scattering. We see something coming up just in the middle of our surface. And then here we see a different pattern. That is actually what we would have expected, because that is the label. Here, something happened. We have some hints that this is thymine. Problem at that time, it was no way going back. to find something like that on a rough substrate, which is totally irregular, is next to impossible. Could be possible today. But what we could say at that time, and we were not really celebrated, but oh wow, you can get a resolution of 100 nanometer and you can distinguish between two different components. So what? Of course, you don't advertise the so what at conferences, but now that we have another solution, I can do that. But why do we do that? Because essentially what you have is you have a substrate that you want to investigate, you homogenize, you mix it. Yeah. And then you put it on a locally different, irregular substrate just to get enough signal. Why on earth do you do high local resolution? You would get essentially the same information. Okay, you would not find that. That would be somehow mixed in here. You would get a very similar resolution. So we were thinking that there must be something better. And the solution is here. So what we do now, in the previous image, we have here a source substrate and then material on it. And then we detect the spectrum. But what we want is different. We want to have actually our substrate unchanged, irregular, locally different, and then we want only one enhancer. This enhancer we put on a AFM cantilever, and then we scan the sample in this focus field. Always have the same enhancer, and now while it looks quite similar, it's a totally different role. Because now we're really looking at local changes on a surface. As long as you don't crash the tip into the surface, it will be always the same. It will be quantitatively comparable. And the resolution, good news, even better. That's too good to be true, right? You have high sensitivity, you have even higher resolution, and you are quantitative. That's too much. No technique can do that. Huh? Okay, so no. What we need is essentially only a plasmonic tip to test that. So it's just silver particle on an AFM. And I can tell a lot, but I think it's really put in the abstract. A fine metal tip brought within a few nanometers. Oh. Brought within a few nanometers of molecular film is found to give strong enhancement of Raman scattered light from the sample. No special sample preparation is required. Enhancement is identical at every sample location, allowing for quantitative self-enhanced Raman spectroscopy measurements. We didn't stress so much the resolution because we really had no clue in the beginning how good the resolution is. This came a little bit later, but the experiment actually worked out pretty well. It was very easy. You measure, it was a dye sample here. We measure a dye sample when the tip was retracted. And then the only thing we changed is we just put this AFM tip on it and found a strong enhancement of the signal. We repeated that several times, always the same result. Okay, this works. And since then, I've never did aperture measurement ever, because that was really a game changer. Yeah. Totally different approach and much more useful. And about the theory and about this kind of evaluation, what's going on, turned out to be even more interesting than the apertures. So high specificity again, high sensitivity, high lateral resolution. At that time, we set particle dimensions, yeah, that we didn't know much better at that time. And then a lot of things we were thinking about were kind of in reach. So the next thing I wrote a proposal. So let's do direct sequencing of DNA. Let's do sequencing of proteins. It's not only that you have to have the high resolution, you need also sample preparation. But the tip properties turned out to be crucial very, very early. So this is actually the setup that we use. So all of our instruments look pretty much the same. There are some details, but you have always an AFM and the sample scanning stage. So we can scan always the tip and the sample. Here we have a high numerical aperture microscope. And the laser system, the laser Raman system here is pretty much straightforward. The only thing is, because of this temperature things, we want to have lines very close to the laser line. And we also play with the polarization of the beam, not just different linear polarizations. We also use vortex beams because it's shown here. What happens if you have, for instance, just linear polarization? The tip picks up a lobe. Because if you have a linearly polarized beam, you have two lobes of Z polarization, and two if you have a high numerical aperture. Yeah? But in this high numerical aperture, this is what you want, and then only the Z polarization is picked up. That is a little bit counterintuitive, because if you have a laser propagating in Z, how can you have a Z polarization? This you get because you focus very tightly. So in the center as such, here, where we have here the intensity, there would be the highest intensity in X direction. This looks almost identical like theory. Yeah. If you use radial polarization, intensity is at the center as predicted. And then, of course, you have to put the tip in here. If you put in a linear polarization the tip in the center, you see nothing. So you have this polarization is really important. Plus, you never know exactly how your tip looks like. And that's kind of also crucial. So then, of course, people think, including us, of course, okay, we have to optimize the tips. This is pretty much the original tip that we used from the very beginning. And I have to say, I'm a bit embarrassed, but this is still the tip that we use today. Not exactly the same one, but the same way of making it. The other ways of making it are most of the time much more elaborate, in using aperture and tip on aperture. So you have to use a focused ion beam. What I rarely see in these papers is the yield of tips, how many are really working in the end. Or you put the Bragg grating in the side of the tip to couple in light. That's a good idea, and you don't have a background. But again, how many tips are working? And this is, and then you have a very expensive tip, and even it works, and then you crash it into your sample. That's suicidal, I guess. So you have these kind of template-based, edge-based, so a lot of ways to do that. But what kind of has that to do with the resolution? So essentially, you always look at the end of the tip to go for the resolution. Now, everybody, or if you have somebody in your group who can do that, you can use COMSOL and other programs, FTTD, to calculate the field intensity distribution. So that's what we did here. Many people did that also before us, no problem. But they all differ a little bit on the shape. Here we try to include that kind of a droplet shape, which is kind of filled with silicon. Then you can have more tips. Doesn't change a lot. Lateral resolution is almost unaffected. What changes is the plasmon resonance, the wavelength resonance. But here, that part where you have high intensity or field enhancement, that is always kind of, I would say, about half of the radius. And you see here, if you make kind of plots here, profile lines here, you see that it's very closely confined. If you see better here, this is about 5 to 7 nanometer full width half maximum. Okay, okay, you have to believe me, but the field decays very quickly. The Raman intensity decays very quickly. So after 2 nanometers, you have almost no signal. So the depth resolution is incredibly high, which can be good or bad. So it also means that you cannot really go very deep into your sample. And then there's just, let's have a quick break. So if you have 3 to 7 nanometers full width half maximum, how many molecules do you have under your tip? Small molecules, I would say 100. When you investigate 100 molecules, are you measuring average properties, or are you measuring kind of statistical specific things on it? Yeah, kind of, would you see a change in isotopic distribution? And we all know that carbon consists of 1% carbon-13. If you have 100 molecules, 100 atoms, is this one thing changing anything or not? So I guess with 100 or more than 100, you're pretty safe. But if your resolution goes below that, then also the way how we look at spectra must change. When we looked at our tips, we saw that they're not spherical. I think we can live with that in terms of simulation. A sphere is a very good approximation. But what kind of was puzzling us, we have this shape, if we go with the TEM, which ends in one atom. And if you think about it, that is very logical because it is impossible to make a sphere. So there is always some polycrystalline samples, or maybe it's even crystalline, and then you have structures that have edges, corners, and facets. And if you have a particle like that and you put it on a surface, there's always the atom, the edge, touching the surface first. If you throw a die, it will end on an edge. What that will have to do with optics is a totally different question. But having that argument told to people with kind of in the terse community was a big issue, was kind of not believed. How can you have single atoms? Which is very interesting because in tunneling microscopy, everybody believes that. Tunneling microscopy, 90% of the tunneling current comes from the first atom, 99% of the tunneling current comes from the first 3 atoms, as a rule of thumb. That is very well accepted. So, and I think we must have single atoms, except when we hammer our tip. Of course, then we will have a flat. But believe me, we really try to avoid flattening our tip. Okay, so that was the kind of how our tips look like. So now let's look a little bit closer. What kind of resolution can we expect? So you saw that kind of 5, 7 nanometers, but probably not the truth because we have this kind of edgy components here. So the real situation would look something like that. You have your atoms distributed, you have edges, corner sides, and so on. And we thought, okay, we still want to model it as a sphere. This is a 2-dimensional Gaussian that is protruding out of it. And what happens then is you get a very similar picture as before when you don't have this protrusion. This is our tip, and here the scale until 4.5 nanometers is exactly the scale that we have when we have no protrusion. That is actually absolutely the same. Here the system doesn't feel any protrusion. But in that part, the start part, which is close to this, protrusion, the signal intensity goes up to 15. So if you look here on the right graph, you have the profile, then you see what's happening. I mean, here, the blue one is, I think, 175. So this is almost invisible atoms sticking out, 150, 120, and 90. So 90 degrees sticking out, well, this would be kind of fully out of the first surface. I don't think that is very stable, but 120 degrees is pretty reasonable because that is the crystal structure for a single crystalline silver particle. And that would be that profile, the red profile. And the full width half maximum here is 1 nanometer. On top of that, this is the off-resonant case. And nobody in SIRS would kind of measure in the off-resonant case. You would always go into plasmon resonance to get as much intensity as possible. So the enhancement and the confinement is even much stronger. So main question here that looks very nice, but it's COMSOL. Yeah? Do we believe that? Well, I didn't really believe that. I thought this is a kind of an artifact. But at the same time, one of our co-authors then had this kind of experiment where he showed that for an icosahedra of 384 sodium atoms, he gets exactly the same result with a full DFT, TD-DFT calculation. Exactly, the intensities are not the same, of course, but the confinement is exactly the same. So this makes really a lot of sense. Plus, then, if that is true, then the FTTD calculation and COMSOL is much faster. Our tips are rough. these are really typical ones. So it's not only the good ones. So here, that one is not the, you won't use that. It's a twin peak. Yeah, so you don't want to use those. So how can we address this kind of coupling? And we made a few experiments on that. And funny is that depending where you set here the enhancer, that's a near field response. Near field response of particle 1 and particle 2. These two particles can give you different resonance frequencies. The intensity looks the same, but I think that is also a little bit arbitrary. And when we do this kind of experiment, what we do is we make an electron microscopy image and we feed that electron microscopy image to COMSOL and do parametrization. What we can do is we simply can then erase the coupling particles to get the coupling contribution. And this was really a surprise to us because it seems that it's only a contribution of 50%, factor of 2. So we expected much more. But apparently this coupling effect in our case is not so strong. The particles seem to be too far spaced apart. But of course, even a factor 2 is important. You can measure a factor 2 faster. That would definitely help. And apparently the quality of the tips that we get is good enough. So maybe only the first 2 or 3 have to be really considered here. And we probably don't have to consider that so much. And then there is another point that we also can make a nice experiment. That is chemistry. How much does chemistry play? What kind of role does chemistry play in terms of resolution? And then it's getting very interesting. This is probably even higher resolution than this plasmonic confinement. So imagine you have a molecule, any one. So this is adenine molecule, and I sketched this grid here, and on this grid we will put an atom, a silver atom, or a silver cluster. And then I measure the alpha ZZ component of the Raman tensor. I calculate the alpha ZZ component of the Raman tensor with different distances. So I don't even switch on a laser. I just look at the Raman response. Because our argument was when we have a tip very close to our molecule, this is not the same molecule anymore. If we bring the tip into the interaction radius, then it's a different molecule. I mean, that argument to all our chemistry colleagues was pretty obvious. What is not obvious, that you can force the molecule then in totally weird conformations. You can put, for instance, a silver atom here on the edge. You could put it in the middle of the ring. You could put it wherever you want. But if you would let the atom go, it would always go to the lowest energy and make some equilibrium. So let's see what happens here. First image, the atom was just 10 angstroms away. And black doesn't mean here it was no Raman tensor at all. Black means here that was the minimum intensity, and the minimum intensity was not changed. The intensity was everywhere the same. Okay, apparently 1 nanometer distance is too far away to induce any chemical changes. That might also depend on the quantum chemical model that you use, but we used one with actually very long ranges. But then we go to 4 angstrom, which is a little bit over the interaction regime. And then we see much higher intensity overall and higher intensity specifically at this position and at that position. And if we go to the repulsive regime, 2.5 angstrom, I'm not saying that we can really go there, yeah? But in theory, you can. You can say DFT go that close. And then you have this even more confined, even higher resolution. It also works with the silver cluster, slightly different because, I mean, the spin conditions is a little bit different in a silver cluster model that we have here. But you see again that they have some higher intensity here and higher intensity here and here. So if you look at the spectra as such, that is even more dramatic. That was just integrated amplification of the whole spectral range. But if the tip of the atom is here beside the ring, actually, and on the ring here, this peak is there, and then it seems that it vanishes. This looks like a totally different spectrum. These 5 spectrum, when I look at them at Raman spectroscopy, I would say these are 5 different compounds. And probably this is the way how we have to look at them. This is adenine with a silver on the left side, on the main ring, on the 6th ring, on the 5th ring, and so on. So what is the resolution then? What is the resolution limit then? Anyone dares? Infinite, right? I'm just limited by the signal to noise ratio and by the positioning of my tip, how precise I can reposition my tip. But realistically, probably by a molecular bond, atoms even, yeah. Yes, but yeah, right. But I will get that, of course, in the course of getting all spectra, right? Plus, I mean, if I compare myself to people of cryo systems, I know exactly what they have on the surface and measure it. So this is for that purpose. It's very theoretical, and I'm not saying that does any good. This is not good for any reaction. But if you want to really push the resolution, of course, you might have to measure an hour, and then the molecule might have drifted. But in principle, that is not limited by the confinement of the laser. This is confined how precise you can control how you position your tip, and then probe it in some way. You don't even have to use Raman. It could be something else. And of course, if you use another DFT basis set, you probably will get a different result. But it's just on paper here. So just to kind of summarize that part, so we have the electromagnetic modeling of atomic features, that we have increased field enhancement, increased lateral resolution. We can look at the coupling, and specifically in that field, there is now a lot of different stuff going on. I think that is very intuitive. That helped us to understand basic concepts that we were allowed to apply. Right now, there is discussion about optomechanical coupling, about, oh no, we have to consider the photons as relativistic objects, which they are anyway. Anyway, so when people come up with refractive indices of up to 1,000 and 10,000, that would help the resolution. There is a lot of things going on that has been kicked off by that, and but I think from a kind of phenomenological point of view, this model helps you to really understand why we have a kind of a high field confinement, and why maybe coupling is not so efficient as we thought. And the quantum chemical model, I'm pretty sure about that. That is really true. What is kind of missing here is a combination, because there is always the light on when we measure. And we kind of neglected that. So far, there is no light on. Okay, oops, sorry. Now, that was some experiments, a lot of kind of theoretical arguments. Now, let's look for some experimental evidence. So, in this case, I will not show you this typical phthalocyanine experiment. So we actually started and do a lot of systems in and with a biological background. Most of our collaborators are from biology. It's very challenging sometimes to kind of convince them to prepare the samples in a way that we can investigate them, and maybe also that it's not always working in water or in buffer. So, but we are getting there. So, for instance, here, protein fibrils, infamous for causing diabetes, causing Alzheimer's disease. We are not looking at these mechanisms, of course, but we just look at the spectra that they have. And when we did that, we came to a point that people said, and we self-doubting, this is irreproducible. We are measuring on these proteins, we always get a different spectrum. Why do we get different spectrum? Every time. Next time we go there, it seems similar, but it is different. And here's what I mean. So this doesn't really look like the same system, right? This is definitely not the spectrum of a fibril. But here there are the amide bands, yeah? From here also carbonyl bands, but not a protein. A protein you would expect looks always the same. Maybe if it's a little bit rotated, but specifically in a fibril, it should not rotate. So I marked here several peaks. Let's go for the green peak. In the first spectrum, no phenylalanine. In the second, phenylalanine. Third, phenylalanine. In the fourth, nothing. And then it never really appears. Oh, well, that might be histidine. Ah, but histidine needs that band as well. No, no histidine. No histidine. Yeah. Oh, wow, here's histidine. 3 positions side by side. Okay, what is the resolution? We had a step size of 5 nanometer per step. And we see more or less an immediate change from nothing to histidine. So I think the step size here limits the resolution. It gets a little bit clearer if you kind of convert the intensities to disks on this spectral line here. So it's kind of almost no intensity, then we have strong intensity, and so on. Here we have this kind of special couple. I would not really discuss these bands because with one band, I would not really trust too much. I would always want to have a pair of bands at least, or like the histidine 3. So the spot size corresponds to the normalized intensity, and I have to write spatial resolution smaller 2 nanometers. Okay, you should not do referee bashing in your in a talk, right? But how on earth we have to say this is 2 nanometer? I don't know. We were saying it is below a nanometer. And actually, I think it should be even below 0.5 nanometer because we see nothing. And after 0.5 nanometer, we are there. So we tried already to be conservative. But 2 nanometer, sorry, I don't see here. But this is in the paper, and I should not say anything else in the paper. But that was totally unexpected because we were expecting maybe 5, 10 nanometer resolution at that time. And that explains also why we had this kind of weird change of spectra. We don't see protein, we see amino acids. Ah, cool. But most of the time, honestly, you want to identify a protein. So it depends what you want. This can be interesting or not. Most of the time when you want to kind of identify a protein, then this is actually bad news, because then it means that you have to measure at different positions of the protein. You cannot simply measure a terse spectrum of a protein. So then this initial, I told you that a 30-year-old proposal, oh, we can sequence DNA, no problem. Not 20-year-old proposal. We can sequence DNA, so this technique can do that. We were even bold enough to kind of write a patent on that. Here is, I think, the most convincing data that this works. So we have here a special sequence. We bought that AC, AC3, AC5, and so on. And here we have the spectra. I'm not sure whether you can see that. So I made essentially the same transformation as before with this kind of disks. So then you see clearly you have 2 peaks. Here's a peak, here's a peak, then we don't have an adenine peak. Here's no cytosine, no cytosine, no cytosine, then we have cytosine. Okay, and it goes on and on and on and on, and we can reconstruct the sequencing. So we have actually a step size of 0.3 nanometers. That means we really get here molecular resolution. Whether this can be ever applied to sequencing is a totally different question. I don't know how many billions they invested in sequencing, so I don't think we can compete. And the other thing is really unfair. For this PCR reaction, if it doesn't work, they simply amplify it by a factor of 2, 4, 8, 16, and then they have enough sample. So they never run out of sample. In proteins, that is totally different. Proteins, they say, you don't need too much. Please give me something back for my precious protein. Not always, but most of the time. And then you are really limited with the amount. In DNA, that okay, I can make more. So that is maybe not the best way to kind of go for, except you have to sequence long DNAs. Then there might be a possibility that this can really compete. And I don't want to kind of end this slide without saying that this has been confirmed also by a statistical approach by the group of Marvin Scully 3 years ago. That's my only non-biological molecule. So this is coronine. This was where we really wanted to push the lateral resolution. How far can we really go? There are experiments under cryo conditions with gap mode, STM, ultra high vacuum, also unfair. Our instruments cannot do that. But okay, so how far can we go? With that molecule, we can definitely not bring it on a metal surface because with a surface diffusion, it would flip around. So what we did then, we calculated actually the spectral response at different positions. And so we see again, like before, we see that different peaks here coming up. And not as much change as in the adenine case, but plenty. What you can see as a general thing is we have much higher intensity at the rim. Also, if we go along that axis, higher intensity, not so pronounced, but higher intensity outside. So what we did then, because we have to measure fast, this is a small molecule, 8 angstrom in diameter, we have to measure fast, and we have to measure with lots of points. So we have to really make a trick here. So we calculated the integrated intensity between 500 and 2000 centimeter minus 1. And then we get an image like that. So outside, as expected, there is higher intensity than inside. Okay, and that is the respective experiment. So this is the 800 picometer. So you clearly see here the coronine. No? Okay. Do you see it here? This is the tip enhanced image. Actually, there is here a brighter ring. Yeah. And there are these kind of dark spots. It's probably a little bit tilted. There are these dark spots. There's only one missing. So we have kind of the 6-fold ring. The 6, 1, 2, 3, 4. This is wrong. 5, 6 dark spots. But you see it better when you actually go. Oops. Yeah, I guess I pressed too often. Okay, when you compare a bigger picture now with STM experiments, and you look for these dark areas, actually here to here to here to here, you get exactly the reconstruction of the surface as you get in an STM experiment. And that I'm not cheating, you see, actually, okay, here I might unfairly guide your eyes, but look here. Again, I'm not saying that it is a fantastic signal to noise ratio, but we had to do this with 2.7 milliseconds per spectrum, per Raman spectrum. I think usually we use 1 second. So this is, I think, fantastic results, but not bio, of course, in that case, but that with biomolecules, this is impossible to do that high resolution. So I think this is where we will stop. We will not go further into that part. So recent developments, I mean, Alexei mentioned it. We started, of course, with the virus here at Texas A&M. I was actually the first virus and terse experiment I did still in Dortmund, my previous position, and believe it or not, there was a grant proposal rejected in 2016. So, but I got it back 2 times a bit later. And kind of drug carrier characterization, which is kind of quite important because these drug carriers are very small. These drug carriers actually are so-called block copolymer micelles that we are using. See here, very small in the nanometer range. And the idea is, and didn't know that. So there are several drugs that are extremely potent. The problem is you don't get them to the organ because they're hydrophobic. You cannot dissolve them. Or you have to give the patient so much of the drug that until it gets to the organ, he's dead, because the other organs are killed by that. So the idea is to encapsulate the drug in something hydrophobic and bring it to the site where you want to have it. And then release the drug inside the cancer cell, inside the liver or whatsoever. And this can be done with block copolymers. I mean, this image, that's from my chemistry colleagues. This is totally misleading because when you look at that, you see, there is a kind of a fancy ring, there is a fancy isobutyl group, there is a fancy biphenyl ring. Here, that is the important part. And there's an N, 50 times. So this would be huge. There's M, that is, I think, 20 times or so. And this is also, no, that is kind of directly connected. So that is the hydrophobic part. And this molecule here is there to be linked, that you cross-link it with this malign D emitter. So then you kind of really have it tied together and the system does not disintegrate in the body because you don't want the drug released too early. You use the reaction that is reversible, and the idea is then to have a reaction that kind of is reversible in a cancer cell at slightly elevated temperatures. So 37 degrees, it stays inside. 38, okay. Help me with Fahrenheit. Or is that okay? Body temperature and 1 centigrade above body temperature, you release it. Yeah? And they have no clue what's happening in the nanoparticle. So that is where we come into the game. And so that is how these micelles look like. These micelles have several nanometer diameter, and that is too thick for us. We cannot look into the core, so we have to freeze fracture it. And we single out one particle and do a 1 nanometer step size TERS experiment, a profile. And this is here along this profile. So this is number of Raman spectra, but this is actually nanometer. And you can clearly distinguish the core, and it's called corona. Sorry, not my invention. Shell, but they call it always corona. And don't be fooled that the intensity, the cross-section of this kind of polyethylene dicol is not as high as the stuff that is in the center. So, and in the center, there are also interesting things going on because there's not full cross-linking, sometimes only half cross-linking, sometimes there are dangling bonds hanging around. And particularly here, we see a region of the interface where almost no cross-linking happens. We are still in the core, but almost no cross-linking happens. But we have this malign emit in the center, so there is a diffusion controlled process. And on a molecular level, we can say that that is impossible to address before. So, of course, it is extremely elaborate to do that with the spectroscopic measurement. But what we combine that now with is kind of elastic measurements with the atomic force microscope that can be done much faster. I don't have the information, but you can compare that. And if you have then a strong change in elasticity or in adhesion, you say, okay, well, something's going on. So now let's look a little bit closer on the Raman spectrum. So this here essentially reveals the completeness or uncompleteness of the core cross-linking process with the resolution even down in the Angstrom range. Yeah. So the last part of the viruses, I will not go into pretty much detail. I will just show one last image where we kind of go now in the future. We extended also from Raman to infrared, where we now here the distinction between influenza viruses and SARS-CoV-2 virus. You see topography is almost identical, but we look here at different wavelengths that we detected beforehand. And we see, for instance, the SARS-CoV-2, we see here this kind of lipid envelope, very strong. Yeah? So with that, I'd like to wrap up. So I think I could show you that we have this kind of theoretical part to help us to understand our experiments better, whether it's coupling, whether it's kind of these protrusions. The experiments indicate that this is indeed possible on the submolecular resolution base, both on ideal and real samples. And what I really skipped, and I don't even have slides here, is our investigations on plasmon properties and temperature that we did also in the recent years. That I'd like to acknowledge my team. Okay. Yeah, here they are. And a lot of cooperations over the years, and of course also funding. Thank you.
If any of you online have questions, raise your hand.
Yep. Because of instrumental drift. If we would measure 1 second per point, and we had, I don't know, I think it was 100 by 100 points. First of all, the measurement in 1 second takes then 10,000 seconds. And in 10,000 seconds, the molecule is in a totally different place. That's practical reasons, yeah.
Can you hear me?
That when you had this question about what the resolution is.
This is Hans calling. Can you hear me?
Right. So you mentioned that there's no limit to the resolution except the signal to noise ratio.
Yeah.
No. But isn't this exactly what you should expect, given that you can collect an infinite number of modes, spatial modes? And of course, the other limit is something when you're in the far field and you're more or less doing measurement on the fundamental mode. Now, if you're in the near field and you have an access to all the modes, then the natural result will be exactly as you said. It will be the signal to noise ratio of your detection system, method of detection.
Well, I think you're referring to the chemical part, right?
No, not at all.
Okay.
I'm referring to this field described more or less in the universal way by equation.
Yeah.
And then this is exactly what you should expect, judging by the information you have collected.
Yeah.
Signal to noise ratio is something that limits the information.
Oh, yeah. Okay.
Any measure of information that you can come up with. Yes. The signal to noise, and eventually this will be exactly as you said. So this should be the result of the resolution.
Well, I think, yeah, that, okay, you can see it that way. So essentially, if you want to sequence the DNA, and then you have kind of slight differences and the left and right edges of your tip, what you're saying is if your signal to noise ratio is good in, yeah, that's true. Yeah. Yeah. Yeah.
Depending on, you have to count for.
Yeah. Yeah. Well, it's actually, the funny thing is it's now possible even to measure the photo-induced forces, so I don't need an optical detector anymore. Yeah. But it's the same.
More questions? Bill?
Yeah,
So,
I can probably do it loudly enough. Can they hear me? The changes in the spectra at different positions. How much of that is due to alterations of the shape of the molecule just because you're trying to measure it, and how much is just that you're coupling to different modes of the same molecule?
That is a good question. I mean, the thing is, first of all, in the theoretical, the DFT calculation, we calculate the molecule at the energy minimum, and then we left it there, and then we simply put the gold atom, silver atom over the molecule, and did not change the geometry. That is, I'm sure, an approximation that's probably not valid. So I think the molecule at unfavorable position will do everything to get away, bend or whatever, and we did not take that into consideration. And what was the coupling into modes? We didn't.
Well, you got the various vibrational modes, but purely if you're in the center of the hexagon, then the modes of the hexagon that are, you know, odd around the ring, you're not going to see sitting in the middle of that. So depending on where you place your mode, you're going to couple you're going to couple to different of the acoustic modes.
Yeah, and I think that is what we see in the changes of the spectrum.
So describing that, I mean, the other question was how much of that may be due to the whole having a football instead of an hexagon.
Well, okay, that is, now I see the point. That we didn't calculate. So for that, we would have to calculate then at every position really how the energy minimizes, even at unfavorable position, then we would have to, but we didn't do that. Whether it does that in reality is a totally different question. It probably does, but that we did not take into account. No. You really have to do that an energy minimization at every position. And this is very costly.
Or else some of the modes could go unstable and indicate that you're getting
Let's see, Hans, did you have a question?
Yeah, I have a question actually. Thank you, Volker. You did a very wonderful talk. Wunderbar. Alles klar, ja. I would like to actually ask, you talk a lot about resolution and not so much about sensitivity. Let's assume you have just a monolayer on your substrate and you scan your tip over this monolayer. Do you see the edge of the monolayer and so on, this stuff? Yeah.
And we have a bit of feedback. I didn't get the whole question, but I think you're asking me whether we see the edge of a, let's say, 2D material.
Of a monolayer, you have your sample on some very clean substrate, and now you somehow cover it, but you don't cover the whole surface. You cover only small parts of the surface. So you are sure that you have monolayers. And now you use your tip-enhanced Raman and go over these blacks of monolayers.
So flake. No. Okay, so whether we can see different flakes of monolayers and discriminate them. Yeah, well, I mean, that is.
He's asking if you can use that to quantify your resolution. You go over the step and you can see exactly how sharp it is.
Yes, I can. I'm pretty sure we can do that. I think that will be then pretty much defined by the step size. But the problem is in that case that you couple with the topography. So that is a little bit different than from a molecule where you have always something. And so the height is not playing a role in the molecule, at least not playing as much of a role in the molecule as it does on an atomic step.
Okay, we can discuss some more on this. Yeah, thank you. Very nice.
It is okay. Okay. So the question was, how do we move our sample on and the tip? Yeah, both with piezo stages. Yeah, but we use, if possible, we use closed loop piezo stages that allows us very high precision in coming back to the same position, except drift. But if you really want to go to images like you have in scanning tunneling, you have to switch the feedback off and measure faster. And we cannot afford that at this time. No.
Okay, let's thank our speaker again. Thank you very much.